So I'm going to give a talk sort of inspired by the contents of a paper I wrote recently with the same title. But I'm not going to try to cover everything at all in the paper. The idea is really more to introduce you to a key idea which has existed for some time since Grandis and Perret introduced it back in 2004, which is the idea of a double adjunction, or an adjunction between double categories. And so we're going to spend quite a bit of time on that, because that's the basic machinery from which we can get various notions of products in double categories. Okay, but first, just a little sort of introductory motivation for this talk. So one of the really fun things about thinking about double categories is that really not all that many people have worked on it, certainly not compared to two categories and bicategories. So there's a lot of really sort of basic and fundamental questions that are still, in some sense, being answered and explored. And in this talk, we're going to be thinking about the question of what are products, are dually co-products in double categories. This is an interesting question just sort of abstractly. It's also very relevant to a lot of interesting examples like double categories of relations and spans and profunctors and so forth, because the notion of product in double categories captures what's going on in those things in the way that, say, bicategorical products don't. So let's, to orient ourselves a little bit, we'll consider some different ways that products appear in categories, and then how they might appear in double categories. So in this talk, I'm going to assume you know about limits and colimits and adjunctions in ordinary category theory. In category theory, there's some different ways to define products, and they're all equivalent. So you can start from the idea of some kind of universal cone. This is the standard textbook definition of products. And there are some other more abstract ways to describe products in categories. You can view them as arising as the right adjoint to a kind of diagonal functor. So it goes from like C to C squared, it's the copying map. So maybe since I don't want to specialize categories, maybe I'll just say right adjoint to copying or deleting functors. This is another way to think about products. And then there's a more sort of unbiased approach where we can think of products as also arising from a right adjoint to inclusion into some kind of category of families. So this is actually the free product. So there's some kind of map from C into something called like fam star of C or something like this would be a commonly used notation. And you can look at right adjoints to that. And I guess I really should be maybe, to be consistent here, I should maybe be saying finite products, and then I'll make this fin fam. So these are finite families of objects in C. And then with that, all of these are equivalent ways. They all ultimately give the same notion. So we have some different places to start when thinking about products in double categories. One approach is to try to directly emulate the approach via yeah?
By right adjoint to inclusion into fam, is that essentially like a fam algebra structure?
It is, but it's like a universal one. But I think it could probably be viewed as, if you think of fam as a monad, two-monad, it probably is some kind of algebra. But here we're getting it from an adjunction. So you can try to directly emulate or in some case try to carry over the cone construction, but it's not immediately obvious to do that because cones are like, in their usual definition, are pretty directly specified in terms of the details of categories, functors, and natural transformations. So it's not immediately clear how to generalize. It can be done, but it's not maybe the most obvious or conceptual approach. But what there is in double category theory, as we'll see, there's a very clean and simple notion of double adjunction, and you can write down this this sort of like copying map for a double category just as easily as you could for a category, and so we can ask for right adjoints to these guys. And that will give a notion of products in double categories. This leads to what's been called Cartesian double categories. But what's sort of interesting about this story is that if you generalize the family construction in what's sort of the most natural way, and later on in the talk I'll explain how to do that and what that looks like, you can get another notion of products in double categories. But what's interesting is that these are not equivalent. And actually having so this is what I'm going to call double categories with finite products, for lack of better way to distinguish these concepts. And this will turn out to be a stronger notion that implies a more flexible notion of product. So that's kind of where we're going. So now, any questions about just the basic framing of that? Was there a question?
The last sentence is interesting. Maybe it'll make sense in the course of the talk. But it's a stronger notion that is more flexible.
I guess what I meant to say is that there are more kinds of products that you're allowed to form in this thing. And that's the sense maybe in which it's stronger. There are more.
So something that is a Cartesian.
So yeah. So maybe to put it, yeah. So.
A product in the first is a product in the second sense.
Yeah. So Cartesian. Wait. No. Sorry. I always get. Every one of these. Well. One of these will give you a Cartesian double category, but not vice versa.
Can you give an example of a concrete double category?
A concrete double category? Yeah. So some examples of double categories. I was going to come to this, but now is as good a time as any. Some examples of double categories that you should have in mind throughout this talk are the double category of relations, for example. Span is another one to have in mind. More generally, spans in some category C, where C is finitely complete. I'm not going to dwell much on this one, but another good example are V matrices, where V is a distributive category. Yet another example, profunctors, and there are other various generalizations and extensions of these sort of things. So all of these are going to have, all of these are going to be double categories with finite products. Yeah.
Perhaps this is also for the end as well, but is the way to think about which one is, like, I don't know, the product or something, like, in some sense, or like which captures better the notion of and or conjunction or something like that?
Yeah. So exactly. So what we're going to get here is that I'm getting a little ahead of myself, but I'll just say it, and yeah.
I'm gonna erase this board, and if you have any questions you want to save for the end,
Okay.
put them up here.
One thing I can say, just to answer that question quickly now, is that a double category with finite products will include both products. So in a Cartesian double category, as we're going to see, you can take two pro arrows, m and m prime, with different source and target, and you can form their product, which goes from x times x prime to y times y prime. And so you can also form these types of products in a double category with finite products, but you can form some other things as well. You can also do, so I'll call these parallel products. So in a generic Cartesian double category, this is the only kind of product you're allowed to form. If you have some extra structure, you can do more stuff. But in this kind of double category with finite products, if I have two pro arrows with the same source and target, I'm allowed to take their product, and that is what is often called a local product, and I write it in this conjunctive notation suggestively because in the double category of relations, this will be the conjunction of two relations. So one feature that you get here is that you can natively express both types of products with this sort of thing, whereas if you want to get local products with a Cartesian double category, you need to assume more stuff, like having an equipment structure. But I'm not going to talk about equipments in this talk. Okay. So that with that framing, let's get into double adjunctions.
Can I ask?
Yeah.
What is the local product, for example, if we take a function?
It's going to take the fixing a pair of objects in your two categories. It's going to take the product of the heteromorphisms between each of those objects. Does that make sense? Yeah.
Two functors to set, and you multiply the two sets.
That's it? Yeah. Mm-hmm. Mm-hmm. Okay. So double adjunction. So in its most general form, a double adjunction looks like this, where f is a colax double functor and g is a lax double functor. And there's an abstract way to see this as arising, or as this adjunction as living in some kind of this is some kind of adjunction, orthogonal adjunction, now often called a conjoint, in some double category whose objects are double categories, and its two types of morphisms are lax and colax double functors, and its cells are some sort of generalized natural transformation. This is a beautiful story. I'm not going to need quite this level of generality, so I'm not going to go into what is needed to sort of set that up. I'm going to specialize to some particular kinds of double adjunctions that we can describe purely in two categorical terms, so it'll take a little less machinery to get off the ground. So depending on how you want to look at it, you can take the following as a definition of a double adjunction or as some kind of theorem stating how this notion of double adjunction, whatever it is, specializes. But in any case, what I'll say is that a pseudo double adjunction is an adjunction in the two-category double. So this thing has double categories, double functors, and for me these are always pseudo by default, and natural transformations. So these sometimes might be called like tight natural transformations or something to be clear at what they mean. They're components that objects are arrows, strict in the strict direction. Yeah.
Sorry, I know what a double category is.
Yeah.
Okay, I know what a double functor is.
Mm-hmm.
I think I don't know what a double natural transformation is.
Yeah. Okay.
Is that an example?
So yeah. So let me just say what the shape of the cells look like to sort of orient what this is. So a natural transformation between double functors f and g, I'll just tell you what its data is and then say kind of in words what the axioms are. So what you have is for each object in my domain double category, I have an arrow. So for a tight morphism, or it'll be vertical in my orientation convention, that goes from fx to gx. Okay, so in particular what we're going to get is that, among other things, a natural transformation between double functors consists of an ordinary natural transformation between the functors between the underlying categories of objects and arrows. Okay, and then for each pro arrow, a cell in E of this shape. So we have F on the top, alpha going between. So okay, so in particular, we're going to have another ordinary natural transformation between the underlying categories of objects, of pro arrows and cells. Okay, and then these are compatible in a certain way, right? The source and target of these component cells are the component arrows from my first one. So that's the data, and then I've sort of hinted at what some of the axioms are. These need to be natural in the vertical direction, and then finally they need to be coherent with respect to the external or horizontal composition. And I won't write those laws down, but if you've ever seen the definition of a monoidal natural transformation, it's essentially the same laws. And in fact, a monoidal natural transformation, if you've seen that, is a special case of a natural transformation between double functors when your double functors have trivial categories of objects and arrows.
Is there an example between?
Well, we're gonna get them from they're about to appear in our definition of a double adjunction, and so we'll see kind of the role they play there. So in the case of but okay, I can kind of preview that for you a little bit, right? So we're going to end up defining binary products in a double category as being right adjoints to the diagonal. So this will have, so this adjunction will have, I don't want to write this, it'll have a unit and a co-unit. And so the, let me get this right, the unit will be the diagonals with respect to this product in the so basically from the unit and co-unit associated with this double adjunction, we're going to get two natural transformations, and those are going to encode the projections as well as the copy paste map. And by the way, this is how it works actually in the ordinary categorical case as well. But we'll see that there's some interesting new things that arise here. Okay, so picking up. Okay, and there are a couple other. So one of the interesting things that happens here is that because of the possibility of co-lax or lax double functors, there are other types of double adjunctions, and what we're going to see is that the kind of double adjunction that goes along with products in this generalized sense is actually naturally a lax one, and that laxness is a fundamental feature of what happens. So we're going to need to consider some other flavors of adjunction. So I'll sort of write them down in a little table here. So so there's so kind of double adjunction. Well, there's this pseudo kind, which I was just describing. So this is an adjunction in some 2 category. So this is in double. And then there are pseudo lax adjunctions, and those are in a 2 category of, so this has, so this guy is the same as this one, except it has lax double functors for its maps. And then similarly, there are co-lax pseudo adjunctions, and these live in the 2 category double co-lax, whose maps are co-lax double functors. So one thing.
If we did lax, co-lax, that we all specialize
Yeah.
upward, right?
And so exactly, so the content of this definition, theorem, whatever you want to call it, is that all of these are specializations of this situation, depending on whether these are restricted to be pseudo. And then there's some sort of magic thing going on here where on the face of it, it appears that both of these double functors in here are lax, but by something called like doctrinal adjunction, it's forced to be pseudo. It's just sort of, that's like a bit of abstract nonsense sort of thing that happens there, but we can take it. In any case, in the adjunctions that we'll be considering, this thing will be pseudo to begin with, so we won't be running into that.
Sorry. Maybe it's not. I'm okay not understanding
Yeah.
this bit, but I actually don't. I forget where pseudo comes in.
Yeah, so the pseudo part is describing the morphisms in this 2 category. And basically, we have 3 different choices. We can have them be pseudo, we can have them be co-lax, or we can have them be lax.
That's where the composition is.
So no, that's where so they're all of these are actually strict 2 categories.
No, she's asking.
Oh.
When you have these double functors, you're talking about whether when you compose and then send it over, that maps to, maps from,
Yeah.
or
So-
is isomorphic.
So
to
it has to
composition
do
taking place
with, so a double functor always strictly preserves composition in the vertical or tight direction. And then it may preserve composition in the horizontal direction only up to comparison cells. And depending on the orientation of those cells, it's lax, co-lax, and if they're invertible, it's pseudo, or if they're even identities, it's strict. So again, this is very analogous to the situation for monodal categories, and in fact, it generalizes it, right? So like, if you specialize to double categories that have a trivial category of objects and arrows, you're going to get back from a lax double functor, a lax monodal functor, and likewise for colax monodal functor. So like, you've seen some version of this concept before. Okay, so one other point here I want to emphasize is that these are just like ordinary strict adjunctions. They're not like bi-adjunctions where the triangle identities hold only up to iso or something like that. So if you were just working with a bi-category, this relatively clean and simple notion of adjunction is not available. This is one of the virtues of double categories, is that they let you work with a notion of adjunction where things hold on the nose and not up to iso. Okay, so this is a nice like kind of conceptual definition. It's useful for proving things about double adjunctions in the abstract, but it is not very good for exhibiting double adjunctions in practice, because there's a whole bunch of data involved in one of these, and you have to construct it all, and you'll be calculating all day if you go about things that way. So there's, just like in the case of ordinary adjunctions, you can see them as existing from some unit or co-unit, but you can also see them as arising from universal properties in different ways. And so the main thing that I want you to take away about double adjunctions is that there's a really nice characterization of them in terms of universal properties that makes it very easy to work with these things in practice. So this, I'm not going to prove it, but I'm going to state it, because this is how we're actually going to reason about double adjunction. So right adjoint, right double adjoint via universal properties. Okay, so given a let's say pseudo, for the sake of definiteness, double functor f. Oops. The existence in choice of a lax right adjoint G is equivalent to the following stuff. So this is going to be generalizing or extending the characterization of adjunctions via universal arrows that you might have seen sometime before. So we're basically going to see that there are two different kinds of universal arrows involved for the two different underlying categories. But what makes this quite powerful is that we're going to see that this actually will uniquely determine the laxators and unitors of G as well. So that will also come from the universal property. So many parts of G are forced by this universal property of being an adjunction. So first of all, we have that for each object y in E, there is a choice of object. I'm going to write it as G applied to Y. G hasn't been defined yet, but the reason for this notation, right, is this is going to define the action of G on objects. And then there's an arrow, epsilon sum y, that goes from f G y to y. And again, the reason for this notation is that this is going to be defining the co-unit of the adjunction. So we're in essence constructing so the full data of this thing.
And then are you basically saying that on the type category there's an adjunction?
Yeah, so all I'm getting to here, right, exactly.
I can do it any way I want. I can do it with universal arrows if I want.
Yeah, this is just a particularly nice way to do it. But yeah, what I'm saying first of all is that that is universal from yeah, exactly, David, from F0 0 to y. So this is indeed precisely saying that I have an adjunction. So by one characterization of junctions in ordinary category theory, this is giving me some kind of adjunction. Would it be helpful if I wrote down this universal property? Okay, yeah, it's actually, I often forget it as well. Let's see if I can get it right. Okay, so I think this says that, so, yeah, right, so given x and d and, yeah, right, so I have some function, or map from G from fx to y. There exists a unique map f from G. Wait, all right, let's draw the picture. So get my right. So the picture that I'm going to end up having is this G, Y, epsilon y. So that means that, yeah, there exists a unique f from x to gy such that this triangle commutes. So like, if we imagine, this is something that is quite familiar, right? If we imagine that, like, we're back in having E be d squared and f be delta, so that G is some kind of binary product, then this is encoding the universal property of the product, because y is now like a pair of objects in D, and this is my cone, and then it's saying that if I have another cone, I get the factorization. But okay, so okay, and then the other part here is, so I have, this is part one. Okay, so basically I'm going to have another universal arrow for each n from y to y prime in E. I have G of n, G to gy, and then I have a cell fgy, fgn, fgy prime, that's compatible with my choice of co-unit arrows over there. So I have epsilon y and epsilon y prime here. And then I have some new cell. So we can see that this is also lining up with the data of a natural transformation, right? Like we were just describing before, right? I've given now what will become the two components of this natural transformation epsilon.
This is the same as the data of a junction between
Yep.
P1 and
Yep. So this is universal from F1 to n, right? And so what this is giving me now is I'm now by some theorem about adjunctions in ordinary category theory, this is giving me now another adjunction between categories. And it just needs to be compatible, and the only requirement on it is that it be compatible with my other adjunction by having these cells have the right shape. Okay, and so what's sort of, and actually that's it. So this is the end of the statement of the proposition. So what it's saying is that given that I can construct this assignment of G on objects, and I can construct the assignment of G and the co-unit on objects and on pro-arrows, that fully determines G on also arrows and cells, and it determines the unit. And that's sort of just coming from ordinary category theory. But then on top of that, it also determines the laxators and unitors of G. And I don't know that I really want to go through that, but the basic idea here is that these guys come with a universal property for that is like this one, but applying for pro-arrows and cells instead of objects and arrows. And by invoking that universal property, you can actually construct what the laxators and unitors have to be. That's sort of the outline of it. And so this is a very efficient criterion that you can use to construct double adjunctions that makes them, once you get used to it, much easier than, say, it's much easier to, say, check that a double category is Cartesian by exhibiting the definition of products on objects and pro-arrows and then checking that the universal property holds than by, say, constructing a symmetric monodal double category, checking a whole bunch of coherence and so forth. So let's actually see how this manifests in the case of Cartesian double categories. So one other comment about this. What's interesting to note here is that with a double adjunction, the thing that naturally comes out of this characterization is a lax right adjoint. That's what you get for free. It's an additional question whether that thing is actually pseudo. But somehow this is showing why it's actually very natural, why lax functors are going to arise kind of automatically in this context, even if you started out maybe thinking you only wanted pseudo stuff. Okay, so with that, we can say that, so this definition is due to Alice Berry in her PhD thesis, which was building on earlier work on limits in double categories by Grandis and Perret. A double category is pre-Cartesian if there are pseudo lax adjunctions. So one of the ones is the one that I've been drawing previously. So this is giving me binary products, and then I also have nullary products. I'll write this I to avoid confusion with more ones. And this is D, and then D is Cartesian if, I'll just say, if it's a pseudo adjunction. So in other words, these right adjoints are actually turn out to be pseudo double functors and not just lax ones. So how does one check this? Well, based on this criterion, you just need to check. So based on what we've just seen, maybe it's worth writing this. Yeah.
I don't know if this is,
Yeah.
if you plan to do this, but I would be really interested in an example, especially because like I can imagine if
Yeah.
something like span or
Yeah.
rel. I know what happens at the one categorical level, and I'm like, and then what is the?
Yeah.
Well, I guess we know. I guess we just don't.
Yeah.
But
I'm actually, I have spans as the example I was going to do because it's very clean. So let's go ahead and do spans.
but if you prefer to do something else first, that's fine.
Well, I think it's good to just to do an example. I'm just trying to decide whether I want to spell out maybe I'll just spell out a little bit. Why don't I? Okay, so why don't I just say, based on this proposition here, which we're just taking for granted, we can deduce that a double category D, and then Sophie will use this to see how to construct products in span, is pre-Cartesian if and only if D naught has binary and nullary products. I mean, i.e., it has finite products in the ordinary sense, and also D1 has the same compatibly with D0. So in other words, what I need to be able to do is take, so in the case of I'll just do the binary products, I need to be able to take two pro arrows with arbitrary sources and targets and form their product. So I need to be able to have an assignment to some new pro arrow. Oops. And then I also need to give the projection. So that my co-unit over here was my projections are living in this co-unit. So I have, if I unpack what's going on there, I have projections that, well, okay, so I've got pi 1, and similarly I have pi 2 onto m prime.
Sorry, I felt really slow about
Yeah.
how those are the
Where are they coming from?
Yeah.
Yeah. Okay. So let's break it down a little more. So I'm going to my co-unit epsilon, which I will suggestively call pi, is a natural transformation from
Oh, I see it.
you see it?
Yeah.
Yeah.
Oh, nice. Very cool.
Yeah.
It goes from x times y, comma x times y to xy. Cool.
Exactly. So secretly, this is in d squared. So this has two components,
Pi 1
pi 1
and pi 2.
and pi 2.
That's beautiful.
So in other words, I just have products in d0 and d1, and these are what my projections for the pro arrows look like. They're compatible with my other ones, and they satisfy the usual universal property, and that's it. So we can give a very efficient and easy construction of products in span, for example.
Is that going to be pre-Cartesian or Cartesian?
Oh, yeah, so this is pre-Cartesian.
And span is going to be pre-Cartesian?
Well, span will actually be Cartesian. So there's two things to check if you want to get to Cartesian. First, you exhibit this, and then you also need to show that the comparison cells between products and external composition, which I can write down the form of here in a second just to sort of imagine what they look like, are invertible. So let's start with the first part. We'll let C be finitely complete. Okay, so if you want, you can think that C is set. It's kind of the most standard choice. Then span C is, well, first of all, it's pre-Cartesian. Why? Well, the underlying category of objects in arrows is just C itself, and that has finite products by assumption. What is the underlying category of pro arrows and cells? Well, that is the that is the functor category from the walking span into C. And as we know and love about functor categories, that has products computed pointwise in C. So in particular, they're compatible with these, and that's it. That shows that span is pre-Cartesian. So very, very easy in the end to verify that. Now moreover, span C is Cartesian. So what do we need to check? So let me just write down in general what it means. So a pre-Cartesian, we'll just end up covering very little of what I said the talk was about, but that's okay. Hopefully you've learned some interesting things about double categories. So our pre-Cartesian double category is Cartesian, if and only if, and this is essentially by definition. So basically, let's do so I'll give myself two composable sequences of pro-arrows. I have a comparison cell. So from the fact that, let's remember that my products here, this is a lax functor from d squared to d. So I am afforded with comparison cells that look like this. I often like to denote these this. So I have some kind of comparison here. And then down here, I exchange the order of these operations. So I have m o dot n times m prime external with n prime. Okay, so this, I automatically get this. Let me not go into directly where it comes from, but this comes from the universal property of the product. So you've probably seen before in your life that like a functor between categories with products is automatically oplax, I think, and via the universal property. So this is the same sort of thing. So this is invertible. So this is one of the things, and then you need a couple others. So there's actually 4 of them total. So you need so this is basically binary products commute with external composition. You need binary commutes with external identities. And then you need likewise for nullary products, those have comparison cells, and those need to commute with the external composition in unit. So it's actually fairly typical that it's actually a bit more work to verify. It's fairly typical that it's more work to verify this sort of thing. Here, just to be a bit glib, why is it true? What's happening is, because this is basically some kind of like limits commute with limits type situation. So specifically, we have products commute with pullbacks. I mean, that's what you end up verifying to show that span is actually Cartesian. Yeah.
Does it mean for a 2-cell in a double category to be invertible?
Yeah. Okay. So this is invertible in D1. So this is invertible in the category of pro-arrows and cells. So in other words, I can exchange these vertically. Does that make sense?
Yeah.
Yeah.
How non-trivial is the compatibility check? Like is there a double category for which D0 and D1 have products with compatibility fails?
Yeah. So one way you can get one of those is to take this. So another example, if I let's take matrices. Let's look at VMAT for V. So generically, I can construct VMAT for any distributive monoidal category V. So let's suppose that the monoidal product is I don't know, like this could be like vect in the tensor product. Like so, the monoidal product is not Cartesian, So not Cartesian monoidal, but also let's just suppose that V has products. So in the case of vect, right, you've got like the tensor product, and then V has products which are like the direct sum. Then VMAT will be pre-Cartesian, but not Cartesian. Yeah. Okay. So I'm about out of time. Let me just let's see what else. Is there any last things I want to say? So I didn't really get to the double family construction. So maybe what I'll just take a minute or two to say what the objects and pro arrows in this thing look like, and then we can imagine how that would lead to a more flexible notion of product, and then we'll stop there. So
Sorry, you didn't answer my question there, right?
I think I did.
I was asking about fails to be pre-Cartesian.
Oh.
Because
Fails to be pre-Cartesian.
like both D0 and D1 have products, but still fails to be pre-Cartesian.
Oh.
Because it's not, the D0 and D1 products are not compatible.
Yeah, can that happen?
Like, is it enough to check?
I mean, I think as long as the source and target functors from D1 to D0 preserve products, then you can presumably make a choice of products such that they are compatible. I guess you could arrange. You could probably cook up some example where D0 and D1 have products, but the source and target functors don't preserve them, and then it would fail to be pre-Cartesian. It's a rather odd. I haven't actually seen that situation come up. It would be sort of a weird thing. Whereas it's not that weird to end up with products that are only lax.
Cospan is pre-Cartesian.
Yeah. Well, it's actually Cartesian.
It is?
Yeah.
Wow.
So we didn't get to this, but yeah, I'll just leave it there for now. Yeah. So let me just say one last fun thing. So I'll just give a hint of what the double family construction is, because supposedly this talk was about that. Given double category D, I can construct this thing called fam of D, and it has, so its objects are a set I together with an indexed family of objects in D. So in other words, this double category, I won't write down what the arrows are, but it will turn out that, unsurprisingly, on objects and arrows, this will be the ordinary fam construction on D naught. That's what's going to end up happening here. So more interestingly, on the pro arrows, so the pro arrows from an indexed family to another one, well, are a span between the indexing sets together with a family of pro arrows that are indexed by these. So I have, so the notation, okay, so I'll write it. So the literal notation is that I have M from X at L of A to Y at R of A for all for A. And then I kind of like to suggestively write this. If you're writing a lot of these things, that gets old. So I often just write MA from xi to yj indexed by A's indexed by things that look like this, where this is supposed to be read as the A maps to I and J under L and R. But anyways, so what this allows you to do, so I can just quickly say what this lets you do that I alluded to at the very beginning of the talk. So parallel, well, in this case it would be coproducts because of the way I've defined parallel coproducts would come from indexing spans that look like this. So in other words, they're the identity span. And then local coproducts would come from ones that look like this. So in other words, all these are sort of tied down so that they all have each the same source and the same target. So that's like kind of some stuff you can do in that situation. So sorry I didn't get to spend more time on that aspect of things, but I hope the discussion of double adjunctions was useful. That's like the key kind of technical tool behind all this, and it's a generally useful thing in all sorts of other situations. So I hope you took something away from it. Thanks. Yep.
Questions for Evan?
Yeah.
Can I ask, how did coproducts show up?
Oh, sorry. Yeah. So basically, I guess at this level of discussion, it's not even clear because I didn't define the arrows or the cells. But normally with the FAM construction, like the standard way of doing this, is that an arrow is going to end up, so an arrow from this will be, it will be a function f naught from I to j together with a family of arrows going from xi to y at f naught of I. And if you it turns out if you take this kind of arrow where the f naught is going in the like covariant direction, that gives you coproducts. And you've got to flip things around to get products, actually. So yeah, sorry, I wasn't very clear about that point. Yeah.
I'm curious about your motivation.
Yeah. So one big source of motivation for a lot of this stuff is that people in the applied category community have often shied away from doing two-dimensional constructions because it can be very painful if you approach it in the wrong ways. So like, it's very natural to want half open systems that are two-dimensional because if one direction of compositionality is something like the maps between your systems, and the other is something like composing open systems along their interfaces. So it's natural to have that, but if you don't come about it with the right machinery, you'll end up having to check do tons and tons of difficult kind of, or like, not mean difficult, but like annoying and long calculations to show that you actually have, say, a symmetric monoidal structure on your bicategory or double category. Whereas if you can exhibit the product structure that such systems have as coming from a universal property, whether it's a product or a coproduct, you can save yourself doing a whole bunch of calculation. And so my paper at ACT last year actually was about how, at least in the case of structured cospans, you can view those as forming a co-Cartesian double category. And by calculations basically is like easy as this one, you can get that. And then you can deduce from that if you want by abstract nonsense that it's also a symmetric binodal double category and stuff like that. But the point is that though that like in category theory we want to put universal properties to work because they're very powerful and economical. But if you're working two-categorically or bicategorically, you often can't see the universal properties that these structures satisfy. But somehow by going to double categories and giving yourself this extra dimension, this sort of theory often lets you find those. Yeah. Yep.
I have a question which threatens to undercut that thesis.
Okay. Great.
Which is that, so if you think of a double category, or if you think about the category of graphs in cat, so like functors from the graph schema into cat, then there's a free double category monad on this category, which just sends like a graph of categories to the free strict double category. It's kind of like a list. It's kind of like a free graph construction, free category construction, but yeah, free double category.
So it's free in the horizontal direction?
Yeah, free in the horizontal.
Okay.
Then you can say a strict double category is a strict algebra for this monad. A pseudo double category is a pseudo algebra for this monad. And then lax and colax morphisms are lax and colax algebra maps.
Okay, that seems nice. But yeah, okay.
I guess my question is like, I wonder how much of this can just be done in two monad land, where you say, I start with some two category, I have a strict two monad on it. Let's look at let's look at a notion of algebra let's look at a notion of Cartesianness or whatever.
Yeah, I think it's a great question, and so I actually do believe that, like, so the viewpoint that's been implicit behind this whole story, like the way we've been looking at adjunctions, is that a double category is two ordinary categories that are tied together by some additional data. So specifically, it's a category or a pseudo category internal to cat, and this notion of double adjunctions kind of, in a way, comes from that viewpoint, right? And so I absolutely do believe that like probably a lot of the things that people have been doing with double categories could be generalized to situations where you have some sort of object internalized in cat. And I even wrote a blog post a year or two ago with some rather rough ideas, for instance, about like how the Groton deconstruction is something that makes sense for any sort of object internalized in cat. And I think that probably similar things are true about the various notions of double product that are being explored. So yeah, I think it's a great question. I think it's a great point of view and one that we should be developing more, because particularly in these sort of undirected kinds of systems, it might be more natural to think that you have some kind of other gadget internalized to cat and not a category. But I very much do think that a lot of the same ideas could be applied. So yeah, okay, cool. I agree with you. But I don't think it undercuts this. I mean, it just goes to show you that the ideas are probably more general than the ones that are presented here. But we're category theorists. We know that they're always secretly more general somehow.
Yeah.
So.
but it's like how the wheel turns. It's
yeah.
Like, we're getting this stuff from double categories.
Yeah.
But this is secretly coming from the two categories.
Yeah. Well.
But anyway.